Hello everyone, my name is Deepanshi from Chemistry Honors Final Year, roll number 76. Today's topic is infrared spectroscopy and mass spectrometry. Introduction to mass spectrometry. Infrared spectroscopy gives information about the functional group of in a molecule, but it tells little about the size of the molecule or what heteroatoms are present. To determine a structure, we need a molecular weight and a molecular formula. Molecular formulas were once obtained by careful analysis of the elemental composition, and a molecular weight was determined by freezing point, depression, or some other difficult techniques. These are long and tedious processes, and they require a large amount of pure material. Many important compounds are available only in small quantities and they may be impure. Mass spectrometry (MS) provides the molecular weight and valuable information about the molecular formula. Using a very small sample, high resolution mass spectrometry (HRMS) can provide an accurate molecular formula even for an impure sample. The mass spectrum also provides structural information that can confirm a structure derived from NMR and IR spectroscopy. Mass spectrometry is fundamentally different from spectroscopy. Spectroscopy involves the absorption or emission of light over a range of wavelengths. Mass spectrometry does not use light at all. In the spectrometer, a sample is struck by high energy electrons, breaking the molecule apart. The masses of the fragments are measured, and this information is used to reconstruct the molecule. The process is similar to analyzing a vase by shooting it with a rifle when weighting all the pieces. The mass spectrometer. A mass spectrometer ionizes molecule in a high vacuum, sorts the ions according to their masses, and records the abundance of the ions of each mass. A mass spectrum is the graph plotted by the mass spectrometer, with the masses plotted as the x-axis and the relative number of ions of each mass on the y-axis. Several methods are used to ionize samples and then to separate ions according to their masses. We will emphasize the most common technique, electron impact ionization, for forming the ions, and magnetic deflections for separating the ions. Electron impact ionization. In the in the ion source, the sample is bombarded by a beam of electron. When an electron strikes a neutral molecule, it may ionize that molecule by knocking out an additional electron. When molecule loses an electron, it has a positive charge and one unpaired electron. The ion is therefore a radical cation. The electron impact ionization of methane is shown next. Most carbocations have a three-bonded carbon atom with six paired electrons in its valence shell. The radical cation just shown in is not a normal cation. The carbon atom has seven electrons around it, and they bond it to four atoms. The unusual cation is represented by the formula CH4 plus, with the plus indicating the positive charge and the dot indicating the unpaired electron. In addition to ionizing a molecule, the impact of an energetic electron may break it apart. The fragmentation processes give a characteristic mixture of ions. The radical cation corresponding to the mass of the original molecule is called molecular ion, abbreviated M+. The ion of smaller molecular weights are called fragments. Bombarded of methane molecules by energic electrons, for example, produces the molecular ions and several fragments. Both charged and uncharged fragments are forwarded, but Only the positively charged fragments are detected by the mass spectrometer. We will often use green type of the invisible uncharged fragments. Separation of ions of different masses. Once ionization and fragmentation have formed a mixture of ions, these ions are separated and b- detected. The most common type of mass spectrometer shown in figure 1215 separates ion by magnetic deflection. After ionization, the positively charged ions are attracted to a negatively charged accelerator plate, which has a narrow slit to allow some of the ions to pass through. The ion beam enters the evacuated flight tube with a curved portion positioned between the poles of a large magnet. When a charged particle passes through a magnetic field, a transverse force bends its path. The path of a heavier ion bends less than the path of lighter ion. The exact radius of curvature of an ion's path depends on the mass to charge ratio, symbolized by m upon z or by m upon e in older literature. In this expression, m is the mass of the ion in AMU and Z is the charge in the unit of electronic charge. The vast majority of ions have a charge of plus 1, so we consider their path to be curved by an amount that depends only on their masses. At the end of the flight tube, in another slit followed by an ion detector connected to an amplifier. To any given magnetic field, only ions of a particular mass are bent exactly the right amount to pass through the slit and enter the detector. The detector signal is proportional to the number of the ions striking it. By varying the magnetic field, the spectrometer scans through all the possible ion masses and produces a graph of the number of ions in each mass. Mass spectrum 1213b mass spectrum. The mass spectrometer usually plots the spectrum as a graph on a computer screen. This information is tabulated and the spectrum is printed as a bar graph or as a table of relative abundance. Figure 1216 is the printed mass spectrum. All the masses are